So we are going to begin looking at electricity by considering the fundamentals of electrical circuits with current and voltage here. So we have a simple DC circuit, positive terminal, negative terminal, with three bulbs connected to it, three filament lamps here connected in what we would call a series circuit. So we have one path for the current to take from the positive terminal around to the negative terminal of this power supply. Now, what's going to happen here basically is these electrons will be repelled from the negative terminal here of this power supply around towards the positive terminal. So we will end up with a flow of electrons which will flow in this direction around the circuit. However, an electric current is simply a flow of charged particles. A movement of positive particles or a movement of negative particles will both constitute an electrical current. And for historical reasons, we've always taken the direction of current, or what we might call conventional current, to be the direction in which positive charges would move around the circuit. So we will label the direction of the current. I here stands for current. We would label the direction of current, conventional current, going from the positive terminal around to the negative terminal, because originally we always imagined the electrical current to be the direction in which a positive charge would move. So even though today we know that in actual fact the charge carriers in electrical circuits are electrons which are negatively charged, we still stick with this convention of the current moving from the positive to the negative terminal, even though, as I say, we know the electrons are actually moving in the opposite direction. When we turn on this power supply here, electrons will begin to move around the circuit and we will have a flow of charged particles. So what will happen is the electrons will experience a force from the power supply. They'll be repelled from the negative terminal and attracted to the positive terminal. And there will be a gradual drift of electrons then around the circuit. Now it's important to realise that all of the electrons, all of the free electrons in the conductor here, will experience a force at the same time. So for one of these filament lamps to light, we don't need to wait for an electron to move from the negative terminal to this filament lamp here. All of the electrons at all parts of the circuit will start moving at the same time. It's a bit like having a tube filled with table tennis balls, and if you push a table tennis ball at one side, then the table tennis balls right the way through the tube will start to move as one pushes on the next one. Same principle here with electrical circuits. In terms of the motion of the electrons, what they will do then is they will experience an accelerating force from the power supply, which will cause them to speed up, but then they're constantly going to be involved in collisions. So what will happen is an electron will accelerate, it will collide with a metal ion somewhere in one of these wires, or particularly in the filament of the filament lamps, and it will slow down. So it's accelerated, it slows down, accelerated again by the power pack, slows down. And so what you will have basically for the electrons as they're moving around the circuit, there will be an average sort of drift speed here, which is around about there. Okay, so they'll have an average speed here, which is basically constant as they move around the circuit. And we can define the current flowing in the circuit to be rate of flow of charge around the circuit. So the current, which is measured in amperes, current is measured in amperes, or amps for short, symbol A, is simply the charge in coulombs multiplied by the time in seconds. We use coulomb, the unit of charge. One electron has got a charge of 1.6 times 10 to the minus 19 coulombs. So the electronic charge is 1.6 times 10 to the minus 19 coulombs. The charge on a single electron is very, very small. So we use a coulomb of charge. Basically a large number of electrons together would make a coulomb of charge, and the current is basically the number of coulombs of charge that passes a point in that circuit every second. Now we can think in a circuit here, what's happening then really is that the charge carriers are gaining energy as they go through the power pack here. And they're gaining really potential energy, electrical potential energy. If you think about it in terms of an electron is repelled here by the negative terminal, and so it has what at that point electrical potential energy. Just as, for example, in a gravitational field, a 1 kilogram mass would have gravitational potential energy at a height within that gravitational field because it's got a force, the force of gravity, pulling on it in a particular direction. Here, same principle, this time the force, instead of a gravitational force, is an electric force. Now if I was to drop a 1 kilogram mass, of course that gravitational potential energy would be converted into kinetic energy. Here, with these electrons, because they're actually constantly colliding with metal ions within these conductors, the electrical potential energy as a charge carrier moves around the circuit is not converted to kinetic energy. The electrons have got a constant drift speed as they move around the circuit, so they're not gaining kinetic energy. What they are actually doing is converting that electrical potential energy that they gain in moving through the power supply into thermal energy, basically, because as they collide with these metal ions, they're causing them to vibrate faster. And as they vibrate faster, then they've got more thermal energy. Thermal energy, or an internal energy of a substance, is a measure of the kinetic and potential energy of its atoms. So here the metal atoms, or you can consider them as metal ions if you want, if you imagine them having delocalized electrons. The metal ions will vibrate faster, they've got more internal energy, more thermal energy as they move faster. So that's really what's happening as the charge carriers move around the circuit. The electrical potential energy that they gained in moving through the power supply is then delivered to the circuit components, usually as thermal energy. So what we can do, we can think about that here. If we just go back to this original circuit, imagine if we had 3 filament lamps in a circuit like this. Let's suppose we were measuring the voltage across these lamps with a voltmeter. First thing is, we connect the 3 filament lamps in series, we turn them on. What we could set is we could ask the question, which of these lamps will actually be brightest? Well, we've set this up here. So if you have a look at this circuit here, before we turn on the power supply, which of these lamps would you expect to be brightest? Now, the student who's studied physics might expect them all to be the same brightness because they're in series, so they'll have the same current through them. The student who hasn't studied physics might think, well, the first lamp here that's nearest to the power supply, maybe that one will be brighter, and they'll get dimmer as they go on. But the student who studied physics might say, well, look, a series circuit, the current through each of these is going to be the same. They're going to be the same brightness, and that would be true if the bulbs were identical. But I've actually selected 3 bulbs here with different ratings. So we're going to turn on the power supply, and we're going to see which is brightest. Now we've turned on the power supply. You can clearly see that the middle bulb is the brightest. The bulb on the left really is barely lit at all, and the bulb on the right is a little bit lit. We can see there it's on, but clearly it's not very bright, so it's sort of intermediate between the other two. Now what we're going to do is connect a voltmeter across each of these bulbs. What we can see here is the voltmeter across the middle bulb is reading about 3.4 volts. Voltmeter across the first bulb reads just over 0.2 volts. And if we connect the voltmeter across the third bulb, which has got the intermediate brightness, we can see that that is reading 0.8 volts. We then connect the voltmeter across all 3 bulbs, and altogether we can see that we have 4.4 volts across the bulbs in total. So that brings us to our definition of voltage, or what I would prefer to call here at A-level potential difference. So if we go back to our circuit diagram, we define potential difference as work done divided by charge. Now let's imagine these 3 bulbs. What we had in the circuit that you've just seen is a power supply of EMF is electromotive force, of 4.4 volts. I know the setting on the power supply might not have been 4.4 volts, but it's not calibrated perfectly. So really we've got a power supply here which had an output of 4.4 volts on the setting that we had. Now, potential difference is defined as work done over charge. So what's actually happening here is that as our charge carriers pass through the power supply, so if we imagine in terms of conventional current, we imagined a 1 coulomb positive charge moving through this power supply, what it would do, it would pick up 4.4 joules of energy. So from the definition of voltage or potential difference, work done over charge. Potential difference is measured in volts. V for volts. Work done is measured in joules. Charge is measured in coulombs. So a volt is equivalent to a joule per coulomb. So what's really happening? If we imagine, let's say in terms of conventional current, a 1 coulomb positive charge went through this power supply, it would pick up 4.4 joules of energy, 4.4 joules per coulomb. Now what's going to happen, that electrical potential energy that it picks up is then going to be deposited in the circuit components. What we're really measuring, when we're measuring the voltage across a component, we are measuring the difference in electrical potential energy that a 1 coulomb charge has between two particular points in the circuit. Now if this connecting lead that we have here between the positive terminal and this first filament lamp has got zero or at least negligible resistance, there will be no energy loss in this wire. Okay, if we can think about resistance as being negligible, we won't lose any energy there at all. And so at this point in the circuit, what we've got is an energy of 4.4 joules per coulomb. Okay, it's not lost any energy in that part of the circuit. But as it passes through this first filament lamp, it will lose some energy. Some of the electrical potential energy is going to be converted into thermal energy in that filament lamp. Now, if we've got 0.2 volts across there, that's telling us the potential difference, the difference in electrical potential energy, that's what we mean by potential difference, across that first filament lamp, measured with the voltmeter, was 0.2 volts. So at this point in the circuit here, each coulomb of charge only has 4.2 joules per coulomb because it's lost 0.2 joules in that first filament lamp. And that really is what we are measuring when we measure voltage with a voltmeter. We're measuring the difference in electrical potential energy that a coulomb of charge has between those 2 points in the circuit. Here we've got 3.4 volts or 3.4 joules per coulomb across this second lamp, and so if we've lost 3.4 there, at that point in the circuit we've got 0.8 joules per coulomb, 0.8 joules per coulomb, and that final 0.8 joules per coulomb is lost in that third lamp, so the electrical potential there is now 0 joules per coulomb. So deliberately, when we did that circuit, we'd actually set it up with 3 different filament lamps that have got different ratings, filaments with different resistances, and because of that they were lit to different brightnesses. But we can see here the brightest bulb was actually the one that we recorded the biggest potential difference across with our voltmeter, because that was the filament in which each coulomb of charge was losing the most energy. This lamp here on the left was hardly lit at all because hardly any energy was being lost by a coulomb of charge when it goes through there, so the brightness was very, very low. So that is what we mean by potential difference. It is simply the difference in electrical potential energy that a coulomb of charge has between 2 points. Voltage is work done over charge. EMF, power supplies, batteries, things like this will give energy to the circuit. So as a coulomb of charge moves through those, it will gain electrical potential energy, but then that electrical potential energy that it's gained will be lost in the circuit resistances. Here, so we're getting a conversion of energy basically due to collisions between the moving electrons and the metal atoms, or metal ions really, in those conductors. In electrical circuits, there is a relationship between the potential difference and the current, which is V equals IR. And this really is the formula that defines resistance. Resistance is the ratio of the voltage and current across a component. Essentially then, if we have a larger potential difference across a component, we will drive more current through it. Okay, if the difference in electrical potential energy across a component is bigger, then more current will flow through it. A little bit like, imagine water flowing down a stream downhill. Basically, the steeper the stream is, the steeper the ground, the faster the water will flow, because for every meter the water flows, it's losing more gravitational potential energy. So the water flows faster. Same principle here. Basically, if you've got a bigger difference in electrical potential energy, a larger voltage, a larger potential difference, then that is going to drive the charge carrier, is going to cause them to move faster. So the electrons are going to go flow faster through that component, and therefore we're going to have a bigger current. Remember, current is just rate of flow of charge. Okay, here's a very good question to test our understanding of the ideas of current and voltage. So what we have is a circuit with a 12-volt battery. So a battery is a series of cells to give us a total EMF of 12 volts. And this circuit really has two branches. We've got the top branch here, which has got three resistors, three 10-ohm resistors in series. Why do I say they're in series? Well, there is one path for the current to take. Whatever current goes through that 10-ohm, whatever charge flows through that one, has to also flow through these other two resistors in order to return back to the power supply. And here we've got in this second branch two 40-ohm resistors. Again, whatever current goes through that 40-ohm has to go through this one. But we can see here the circuit branches at this point here. So as a Coulomb of charge flows from this point, from the power supply, it gets to this point, it's got a choice. It can either flow through this branch and back to the power supply, or it can come this way. Some coulombs of charge are going to take this route, some are going to take this route. What we know is, as a Coulomb of charge, remember the conventional current will be going from positive to negative. So on a battery, basically the longer terminal here is the positive one. Imagine you can split it in half and make a plus out of it. So there we've got our positive terminal, there we've got the negative terminal. So imagine a Coulomb of charge coming through this power pack. If the EMF is 12 volts, or if you like 12 joules per coulomb, remember a volt is a joule per coulomb, our Coulomb of charge will have 12 joules of energy at this point, so the potential there is 12 joules per coulomb. We assume the connecting leads have got a negligible resistance, so each Coulomb of charge has still got 12 joules per coulomb at this point. Now, if we want to work out what this voltmeter is reading, what we really need to know is what is the electrical potential going to be at these 2 points, because the voltmeter, remember, is just going to read the potential difference. So if we imagine our 1 Coulomb of charge coming this way, let's suppose it decides to go through this top branch here. Well, these 3 resistors are equal. They're equal resistances. So one would expect them to share the energy equally between them. So each Coulomb of charge here presumably would lose the same amount of energy in each one. If they're in series and they're identical resistances, they will share the total potential difference equally between them. So what we would expect here at these 2 points in the circuit, at this point we would expect 4 joules per coulomb to be lost here, 4 volts across that resistor. So we would have 8 joules per coulomb at that point in the circuit. By the time we get to this point in the circuit, we've got 4 joules per coulomb, and there we've got 0 joules per coulomb. So Coulomb of charge comes through here. If it decides to go through this top route, it's going to lose 4 volts, 4 joules per coulomb in each of those 3 resistors. Now, let's suppose a different Coulomb of charge comes through and it gets to this point, and it decides not to go through the top branch but to come through the bottom branch. That particular Coulomb of charge will also have 12 joules per coulomb. It's not lost anything travelling between the power pack and this point here because it's not had to go through any resistances. Assuming the connecting leads have a negligible resistance, it won't lose any energy in those at all. So this Coulomb of charge has still got 12 joules of energy at this point. Now these 2 resistors, although the larger resistance values, they're both equal values, so one would expect that this Coulomb of charge again will lose the same amount of energy in each of these resistors. Each of these resistors will have the same voltage across them. So if it's got 12 joules per coulomb there, it will lose 6 joules per coulomb in this resistor and 6 joules per coulomb in this one. So the electrical potential there will be 6 joules per coulomb, and here it will be 0 joules per coulomb. So the question is now, what is our voltmeter going to read? The voltmeter is going to read 2 volts. It will measure a difference in electrical potential between 6 volts, 6 joules per coulomb, and 4 joules per coulomb, or 4 volts. So the difference between those 2 potentials, the potential difference, is 2 joules per coulomb, or 2 volts. Now while we're on this, one thing to realise here then is that if we've got a 12 volt power supply, notice both branches, both the top and the bottom branch, will both have 12 volts across them. Again, some students will make a mistake here. They think the top branch might have 6 volts and the bottom branch might have 6 volts, but no. As a Coulomb of charge comes through here, it's going to go through either the top branch or the bottom branch, but not both. So it will either lose its full 12 joules in these top resistors, or it will lose its full 12 joules in the bottom resistor. So each branch will actually have 12 volts across it. Each branch will have a 12 volt potential difference.